We've been using linear approximation to sort of think about explicitly about the input of a function near the base point and the resulting output. But there's another way we can think about linear approximation, and that's rather than emphasizing the input and output of the function, we can emphasize sort of the change that results by moving a little bit away from our base point. So to do that, let's take our linear equation, our linear approximation formula, which is this right here, and let's just rewrite it. But instead of writing things in terms of x and the base point, let's write things in terms of the change in x. So the change in x is just how far x is from the base point. So x is the base point a plus delta x. We can rearrange this to get an expression for delta x. Delta x is just x minus a. Well, you can see that this part right here, x minus a, that is delta x. Whenever we wrote down a linear approximation, we were writing delta x. This part in parentheses represents how far you've gotten from the base point. Also, what we could do is, since we have delta x showing up, you should also expect the resulting change in the function to show up. Well, if we have a particular x value that we're starting with, and then we move over an amount delta x, right, the place we start, the height of that spot is f of a, and the height we end up at is f of x. So the change in the function is just the difference between these two. So that would be delta f, but that's f of x minus f of a. And we can make that show up by just subtracting f of a from both sides. That's going to move this f of a to the other side. So then we get f of x minus f of a is approximately this derivative, the derivative at the base point, times delta x. So here we have delta f is approximately dy dx evaluated at the base point times delta x. And maybe instead of y, I should be writing f. Let me write f instead of y. Okay. So what this lets us do is approximate how much a function changes. You just take the change in x causing the change in output and multiply it by the derivative at the x value that you started at, which is the base point in this situation. So what's happening here is the actual change in the function is the difference between these two values. But if you look at what's on the right-hand side of this approximation, this derivative, that's the slope of the tangent line, as always. And we can sketch the tangent line like this. And delta x is our horizontal move that we've made here, so that's this distance here. Now when you take the slope of a line and you multiply it by a run, you get the corresponding rise for the line. And that's this blue distance here. So this is df dx at x equals a times delta x. And you can see that although the blue distance isn't equal to this vertical red distance, it's pretty close. The piece that we're missing is just this little gap between this black dot and the blue bar. And in fact, the smaller that delta x gets, the better this approximation becomes. So this approximation is only good when delta x is very small. Okay, now often this blue bar, it gets called dx, or I'm sorry, df. And delta x is often also called dx. So we can write this as delta f is approximately df. And df is just df dx times dx. Right? Dx and delta x are really the same thing. So So let's use this idea to approximate the change of a function. So suppose we know that there's some mystery function y, and its derivative at x equals 4 is minus 3. And suppose that we change our x value by negative 0.05. Let's approximate the resulting change in y. So the resulting change in y, we can't know what it is exactly, but it is approximately dy. And dy is dy dx at the place we started with, which is x equals 4, times dx. All right, well, the value of this derivative, that's given here, that's minus 3 times dx. Remember, dx is really the same as delta x in this situation, so that's minus 0.05. And so doing this arithmetic, this is 0.15. So the resulting change in y is approximately 0.15. Now this is an approximation, but remember, the smaller delta x is, the better the approximation is, and this value for delta x is pretty small. All right, so this definition that we made, that df is df dx times dx, these df and dx by themselves, these are what are called differentials. So if we have y as a function of x, then the differential of y, that's dy, is the derivative of y with respect to x times dx. Or if you like prime notation, you can write it this way. And we'll talk in a second about what exactly, or how to think about what this dy thing is. But first, let's just do an example. Let's calculate dy when y is x times e to the x. So just by definition, dy is dy dx times the differential dx. And this dy dx, this isn't a ratio of differentials, this is a regular old derivative. So we can actually explicitly calculate this derivative. We have to use the product rule, so derivative of the first one is 1 times e to the x with no derivative, plus x times the derivative of e to the x, which is e to the x. So there's our differential. So what does a differential actually tell you? So what does this kind of equation mean? You know, before now, I've insisted that dy and dx don't really mean anything on their own, but now I'm telling you, well, they do mean something, and here's what they mean. But what does this mean? Well, the way to think about this is that any differential, so d of x, how you should think of this is a very small change in x, or a small bit of the x-axis. And dy, well, dy is the same kind of thing, but in the y direction. dy is a small bit of the y-axis. And you know, in general, the small bit in different directions don't have to be related in any particular way, but if y is a function of x, then a small bit on the x-axis sort of gets turned into a small bit along the y-axis. So here's dx and here's dy. And because y is a function of x, there's a relationship between these two little bits in each direction. So to know what that relationship is, it depends on how much this part of the graph is slanted. But that's exactly what the derivative tells you. So the derivative is really a translation factor that tells you how much a change in x gets magnified into a change in y. So let's have a closer look at that. I kind of think of a derivative as being kind of a sensitivity factor. So for this example here, this m here, this is the derivative at this base point. And now, so our base point is at x equals 1, and the corresponding output is also y equals 1. Now this slope is small, so that means if I move this green point side to side, this green point will move a lot, but the corresponding change over here in the y direction will be small, and that's because this slope is small. So a small derivative is a small sensitivity. So small sensitivity means large input changes only produce small output changes. And we can see this happening. So along the red line segment, the green point moves a lot, but that large change is sort of suppressed by the small sensitivity, or the small derivative, to produce only a small change in the y direction. Now if we change this derivative to be large, oops, here we go. So now if we make this derivative larger, 2.2 maybe, the size of the changes in the x direction are still the same, but you can see the resulting changes in the y direction are much larger. So y is much more sensitive to changes in x, and that's because this derivative, this sensitivity factor, is much larger than it was before. Now all of this is true even if we shrink the size of this, this red bar down here. So right now it's set to 0.4, but 0.4 to both sides of our base point. But if we shrink it, you can see that it's true that this blue bar is now smaller, but compared to the red bar, it's actually, in proportion, it's just as long as it was before we changed the this range. And the proportion of these two, that's exactly the derivative. So another way to think about what the derivative is telling you, other than just a slope, is that it's a sensitivity factor or a magnification factor. It tells you how much changes in x get magnified into changes in y.